ना साइड से कट गया। तो नहीं ठीक है, ऐसे कुछ नहीं हो रहा, कर रहा हूँ मैं, हैप्पी कर रहा हूँ।
Hi, somebody. Can you hear me? Hi, can you hear me?
Yes, you are audible. Can you do a quick mic test again?
Yeah. Can I try to share a screen?
Yes, yes.
Yeah, it seems we can see the screen.
Hello, Jyongyang. Can you do a quick mic test? We want to see if you're audible here.
Yeah, so can you hear me? Hello, hello, hello there.
Yeah, I mean, it is still a bit low. You might have to speak up a little bit.
Yeah, I can try to
This
speak
is good.
out.
This is fine. This is fine. Yes.
Oh, yeah, thank you.
Thank you.
Hi.
Talking before. Oh, I'm okay. But I've tested myself. Hello, morning. You hear me? Can you
Yeah, I can hear you.
understand me?
Yeah, morning.
One more minute, and then we start really punctual. Oops, I run out and tell them. Guys, the session starts, just to inform you. You're Jion Young.
Yes.
All right, I think we are getting ready. Good morning, everybody. Welcome to the last day of this beautiful conference. This session has now two talks related to applications and relations of satisfiability to quantum computing. And I'm glad only unfortunately John Young couldn't technical problems come here. So therefore, we have the first talks online about quantum circuit mapping based on incremental and parallel sat solving. Please. Thank you.
Thanks for the introduction. Hi, everyone. My name is John. I'm going to present our work, quantum circuit mapping based on incremental and parallel set solving. So this is a joint work with Yaroslav, Yunon, Moraine, and Bruno. So there is compelling evidence that quantum computing can solve certain computational problems exponentially more efficiently than classical computers. And therefore, quantum computing has demonstrated promising results in applications including cryptography, finance, and medicine. However, the practical realization of quantum computing still faces many challenges, including limited qubit connectivity in quantum computer and noisy quantum operations. The figure on the left represents a qubit connected graph for a quantum computer. Every vertex represents a physical qubit, and the edge indicates the connectivity between two physical qubits. So the quantum hardware requires every quantum gate to operate on adjacent physical qubits. But from the graph, we can see not every pair of quantum physical qubits are connected to each other. And this disconnection decreases the ability of quantum computers to execute arbitrary quantum circuits. So on the other hand, the figure on the right represents a quantum circuit. Every horizontal line indicates the lifetime of a logical qubit, and the box on the line indicates a quantum gate. So for example, the gate labeled H is a 1 qubit hard gate, while the box labeled R pi by 2 and a solid dot connected by a vertical line represent a 2 qubit controlled rotation gate operating on Q2 and Q3. So the fundamental uncertainty in quantum theory determines that every quantum gate suffers from an amount of error, and this error accumulates over the execution of gates. In order to control the error of the circuit output within a reasonable range, we have to restrict the length of executable quantum circuits. So fortunately, these hardware challenges can be mitigated at a software level by compiler optimizations. And in this talk, we are going to solve one critical step in the compilation, which is called quantum circuit mapping. So let me use an example to illustrate the quantum circuit mapping problem. So suppose we want to use the quantum computer on the left to execute the quantum circuit on the right. And to achieve this, a circuit mapping procedure must be performed by a quantum compiler. The circuit mapping consists of two steps. The first is initial qubit placement. The second step is qubit routing. So during the initial qubit placement, the compiler maps every logical qubit in the circuit to a physical qubit on the computer. So for example, we can map the three logical qubits Q1, Q2, Q3 as shown on the left figure. And then to execute a quantum circuit, the quantum hardware requires the qubit operands of an executable gate must be placed on adjacent physical qubits. So suppose we want to execute the first 2-qubit gate operating on Q2 and Q3. So looking at the graph, Q2 and Q3 are adjacent because they are connected by an edge. Then this gate can be properly executed. So here I want to mention that the 1-qubit gate can always be executed because there is no issue about the connectivity between its qubit operands. Then let's move on to the next non-trivial gate, the R⁴ operating on Q1 and Q3. So in the graph, Q1 and Q3 are connected, therefore this gate can also be properly executed. So finally, we move to the last non-trivial gate, the R⁴ operating on Q1 and Q2. Look at the graph, the Q1 and Q2 are not adjacent, therefore this gate cannot be trivially executed. So if we analyze this quantum circuit, we can find that the circuit requires every logical qubit to interact with the other two. However, in the graph, no subgraph forms a 3-qubit ring that would allow every pairwise qubit interaction. So which means that no matter which initial qubit placement we choose, there is always a non-adjacent 2-qubit interaction that is not supported by the quantum computer. And this gap necessitates the second step in the circuit mapping, which is called qubit routing. So when the qubit operands of a gate is mapped to non-adjacent physical qubits, the quantum compiler performs qubit routing to remap the 2-qubit operands to adjacent physical qubits before scheduling that gate. And qubit routing is performed by inserting swap gates, as a swap gate is a special 2-qubit quantum gate that exchanges the states between 2 qubits, and it affects the gates scheduled after it. So for example, on the bottom right, we use 2 crossing connected by a vertical line to indicate a swap gate, and it exchanges the states between Q2 and Q3. The gate following the swap gate originally operates on Q1 and Q2. But after inserting a swap gate, it now operates on Q1 and Q3 because Q2 and Q3 exchanges their states. So if you look at the graph, the gate originally operating on Q1 and Q2 cannot be executed because Q1 and Q2 are not adjacent. But after inserting the swap gates between Q2 and Q3, the gate now operates on Q1 and Q3, which are adjacent in the graph, and therefore this gate can be properly executed now. So a quantum computer's ability of executing quantum circuit is limited by the connectivity between physical qubits, but we can always insert swap gates to work around this limitation. However, the inserted swap gates enlarges the quantum circuit, and it increases the accumulated error of the circuit output. So in order to work around this limitation and control the output error at the same time, the problem of circuit mapping aims to minimize the number of inserted swap gates during the compilation. And this is a problem we are going to solve in this talk. So there are 2 popular approaches to quantum circuit mapping problem. So the first is a heuristic approach. It usually tries to optimize the metrics defined by human in order to find a near optimal solution. So the famous approaches include Sabri and TCAT algorithms. So in industry, quantum compilers, heuristic approach are the most popular choices because it provides fast compilation speed. However, it has been shown that the swap count from the heuristic approach can be far from the optimal value. Therefore, another line of work focuses on solver-based approach, which are the complete algorithm to search for the minimum swap count. And the existing work include a max set-based approach, SetMap, and an SMT-based approach called TPOSQ2. and TBSQ2 is a current state-of-art solver-based approach. And these approaches would eventually return the minimum swap count, but it usually requires a long time to run. So in this talk, we present a set-based approach for quantum circuit mapping problem. So it's a fast method to find the minimum number of swap gates in quantum circuit mapping, and we name the tool SetMapper. So SetMapper iteratively decreases the swap gate count S and check the feasibility for S using a modern set solver. Here is a framework of SetMapper. So given 3 inputs, a quantum circuit, a quantum computer, we use QPU to denote a quantum computer, and an initial upper bound on the swap count. The SetMapper encodes the circuit mapping problem into a set formula in CNF, and a set solver takes the CNF as input and checks the satisfiability. So a satisfiable assignment means that there is a valid mapping that uses at most S swaps. And in this case, we further reduce the swap count S and continue the loop to search for a mapping with fewer swap gates. And we exit the gate when the solver returns and set, which means there is no valid mapping with that many swap gates, and we cannot further reduce the swap count. And finally, we decode a mapped circuit with the inserted swap gates from the best result we have obtained so far. We now present the key encoding ideas for mapping a quantum circuit to a target quantum computer using a given number of swap gates. So the first important notation is transition step. So we consider the quantum circuit mapping in different temporal steps, but instead of using the actual time step in the circuit that increase gate by gate, we define a transition step T that increases only after swap gate insertion. Therefore, the qubit placement changes only when the transition step increases. So we start with an initial qubit placement at step 0 and move to step 1 only after inserting the swap gates to update the qubit placement. And we use a Boolean variable CT key to indicate whether the edge key is selected to perform a swap at step T. And the variable is true if the edge is selected, and otherwise it's false. And we use a Boolean variable OTG to indicate whether the gate G has been scheduled by step T. So if the OTG is true, it means that the gate G is scheduled at step I for some I less than or equal to T. So for example, in the circuit below, for the gate R pi by 4, the variable O1 is true because it has been scheduled by the step 1, and it's particularly scheduled at step 0, which is less than step 1. And our target is to make sure all the gates has been scheduled by the last step. That is, the variable O is true at the last step for all the gates. We then present the constraint on swap gates. During the transition, multiple swap can be performed at the same time if there is no conflict among them. So we avoid swaps on adjacent edges because they share a common vertex. So for every step T, and any 2 edges key and key prime sharing a common vertex, as shown on the bottom right, we assert the variable CT key and CT key prime cannot be true at the same time. So on the other hand, since there are at most as many swaps, so the sum over all the CTK variables must be at most S, and we use a cardinality constraint to encode it. So finally, let's investigate how to solve the encoded CNF efficiently in SetMapper. So basically, we can use any state-of-art sequential set solver like KSET or Cadical to solve it. We can also embrace the recent advance in parallel or cross-solving techniques and use a competition-winning parallel set solver like MATLAB or ParquetSet RS to solve the encoded CNF. And after that, we further ask the question, like, can we benefit from the incremental solving either? So the answer is yes. So if we look at the framework, we find that only the at most key cardinality constraint on the swap count varies over the iterations. So probably we can benefit from the incremental solving where a series of similar input formulas are given. But before that, let me first introduce an incremental encoding for this cardinality constraint, which is called totalizer encoding. So totalizer encoding is an encoding for cardinality constraints with varying bounds. So on the bottom, we present an example to encode the kinetic constraint L1 plus L2 until L5 is at most key. And the figure illustrates the encoding structure where every node is represented by a name and a list of variables. And a leaf node represents an input literal. So for example, the node C with input literal L1. The root node includes the indicator variables for the sum of the input variables. So for example, assign O2 to true means that at least two variables from L1 to L5 are true. While a false assignment means that at most one input literal is true. And every internal node represents the intermediate sum over its two children. So for example, the node A represents the sum over the variables from C and D. And the variable A1 and A2 indicates whether this sum is at least 1 and 2 respectively. Then, following this structure, we can encode the propagation of sum. So for example, when both A1 and B1 are true, which means that in the left subtree, at least one input literal is true. While in the right subtree, at least another input literal is true. So we can infer that O2 must be true, which means at least two input literals are true. So similarly, we can write down the encoding for other quantities. And finally, in order to encode the at most k constraint, we just need to assume the unit clause OK plus 1 is false, basically saying that no k plus 1 literals can be true at the same time. And in our application, we are particularly interested in the at most k constraints with iteratively decreasing bounds. And since the not OK1 implies not OK2 for K1 less than K2, since less than K1 always implies less than K2 for K1 less than K2. So we can add the unit clause for a smaller bound without deleting the previous one. So for example, we can add the clause not OK1 without deleting the clause not OK2. And this technique is called incremental strengthening in the literature, and we are going to utilize this technique in our method. Now let's come back to the incremental solving for set mapper. At every iteration, we use the assumption not OS plus 1 to indicate at most S swap gates. And after reducing S to S prime, we only need to replace not OS plus 1 with a new assumption, the not OS prime plus 1, to indicate the new bound. So as a result, we can avoid repeating, encoding, and reading the whole thing F at every iteration. And it also allows the solver to reuse the internal state and learn clauses from the previous call to reduce overall runtime across iterations. So finally, we can use any state-of-art incremental set solver like Cadical to solve it. And it indeed showed promising improvement in our empirical evaluation. So now, given the improvement from parallel and incremental solving individually, we may wonder whether the set mapper can benefit from the best of both worlds by combining incremental and parallel solving. So in the following slide, we are going to give an affirmative answer to this question by presenting an incremental and parallel set solver. Since there is no existing incremental and parallel set solver, so we extended the state-of-art parallel set solver bucket set RS to support incremental solving and named the resulting solver Inc bucket set. So here is the framework of our solver. So Inc bucket set takes the CF as input and initially forks multiple solvers to run in parallel. In our implementation, we use KSet with different configurations as the underlying set solver following the bucket set RS. And every solver keeps an individual copy of the input CNF and maintain its own clause database throughout the running. And during the solving process, different solvers communicate with each other by exchanging important learned clauses to facilitate the global solving. And when a solver finds a solution or proves unset, a global termination signal is sent to the other solvers, and all the solver threads join the main thread. Then we output the result in the main thread and continue the incremental solving by forking multiple solver threads again. And every solver adds the additional clauses file to their clause database and continue to solve the input formula from the previous state. So for Inc bucket set, The underlying set solver packet set does not support the solving with assumptions, but in our application, assumptions are not required. So adding a unit clause across incremental iterations is sufficient for SetMapper to lower the swap count because of the incremental strengthening provided by the totalizer encoding. And our implementation allows Inc parquet set to add these extra clauses across incremental iterations. And in the future, the Inc parquet set can be extended to support assumptions as a general incremental and parallel set solver just by replacing the underlying solver key set with Cadical. So finally, we evaluate our method in practice. We implemented a prototype of our method and compare it with the best solver-based method, TPOSQ2, and the best heuristic method, TCAT. And we set walk clock time limit to 1800 seconds and used 16 CPUs for all the parallel solvers. And the evaluation was conducted on a benchmark of 78 instances, ranging over 2 quantum computer devices and 3 quantum algorithms with various number of logic qubits. We first define 3 metrics to measure the performance of swap count optimization for TBSQ2 and SetMapper. Here I want to mention that lower is better for all 3 metrics, and both TBSQ2 and SetMapper start with an initial bound on the swap count obtained from the heuristic approach TCAT. So the first metric is failure ratio. It's a ratio of instances where no improvement against the heuristic approach TCAT is observed. The second metric measures the quality of the swap count, called swap ratio. It's a ratio of the best swap count to that of TCAT on average. The last one is median runtime. So it's the median runtime across all the instances. Sorry. Yeah, so the following table summarizes the comparison between TBSQ2 and SetMapper. The first row presents the failure ratio, where the TBSQ2 had no improvement on 81% instances, while SetMapper only failed on 24% instances, achieving a reduction of 57%. Yeah, so remember the lower is better for all the metrics. The second row is swap ratio, where TBSQ2 achieved a ratio of 0.8, while SetMapper lowered the ratio to 0.74 by an improvement of 6%. Finally, the median runtime of TBOSQ2 is above 200 seconds, but the SetMapper's median runtime is just 9 seconds, which achieves a reduction of 26-fold reduction compared to the TBOSQ2. So another table compares the performance for SetMapper using different underlying set solvers. And particularly, we aim to benchmark the performance from incremental and parallel solving techniques for SetMapper. So in the table, every column indicates SetMapper equipped with a particular solver. So for example, the first column, KSET, is a state-of-art sequential set solver without incremental and parallel solving techniques. Cadical refers to using the set solver Cadical in incremental mode. And PBOP is a non-incremental cloud sharing based parallel set solver. And Inc parquet set is the incremental and parallel set solver we introduced in this talk. Remember, lower is better for all 3 metrics. So the table shows that the SetMapper equipped with Inc parquet set achieved the best performance. So particularly, both Cadical and PBOP outperformed KSET. So which means that which reveals the individual benefits from incremental and parallel solving respectively. And finally, the combination of incremental and parallel solving benefit allows Inc parquet set to benefit from the best of both worlds. So in conclusion, in this work, we propose an efficient set-based method for quantum circuit mapping problem. So we design a novel set encoding for determining the satisfiability of mapping a circuit with a given swap count. We then develop an efficient implementation to solve the encoded CNF by combining incremental and parallel solving techniques. And empirically, our method is 26 times faster than the best solver-based method and surpasses the heuristic method in 76% of the instances. So with that, I want to thank all of you for attending my talk. Any questions?
Thanks a lot for this very clear talk. Yes, Dominic, please.
Thank you very much for the nice talk. I really like that you harnessed the potential of parallel SAT solving there. I would like to make you aware that Malop does support incremental SAT solving, and not only with assumptions, so but also with clauses. So yeah, this is not published at a conference yet. It was in my dissertation last year, and I used it for planning so far. But I think this would also have potential. So you could raise that to a distributed level even, and try that out. So if you're interested in that, then yeah, we could talk about that. And an important question, I think, how many cores did you use? Did you say that?
16. We use 16 CPUs for all the parallel SAT solvers.
16. Okay.
Yeah.
Okay.
I think then there was over there, and then you are the third, Moshe.
So thank you for the talk. I wanted to ask, so these cardinality encodings are like an important part of the encodings, right?
Yeah.
I just wanted to ask, and there have been a lot of cardinality encodings proposed in literature. I just wanted to ask about the reasoning for choosing this particular cardinality encoding, and if you have also tried with different encodings.
Yeah, so I didn't test a lot. So at that time, I just want a kinetic constraint with supporting the very response. So I found this totalized encoding. Yeah. Do you know, is there any other kinetic constraint supporting this very bonds?
I think so, but I would have to look into it again. But I'm pretty sure.
I think Moshe, please, yes.
How many qubits are you able to handle?
It depends on the structure of the quantum computer and also quantum circuit. So for example, for the easy structure, suppose we have a grid, right? They're on a horizontal and vertical line. In that case, I guess it's very easy to scale to like 50 or maybe even 100 qubits. But giving, for example, the structure as I shown in the final slide, this kind of complicated structure, and also for some complicated quantum circuit like quantum Fourier transform, it's hard to scale to 20 qubits. So it heavily depends on what kind of quantum computer and what kind of quantum circuit you want to use.
And how close is this number to the number of qubits needed for realistic applications?
I don't think we have
just to give you an example. Just to give you an example, for
yeah.
Shor's algorithm, the estimate is that we will need about 100,000 qubits because of the error correction.
100,000 qubits.
That's for Shor's algorithm. But so I wonder, if you look at your application, what is the number? What is the realistic number of qubits that one will have to solve for this to be applicable to applications?
I think if we use a very simple computer, we can scale to hundreds of qubits. But I have no idea whether the Shor algorithm can be run on such a quantum computer.
I'm not asking for Shor's. For your application, you listed some applications.
Yeah.
You try to look at them in a realistic setting and get an estimate of how many qubits are needed. Then we'll get some sense. You're able to solve problem with, let's say, even 100 qubits.
Yeah.
Is going to do anything towards actually building, useful quantum circuit? This is my question.
I think most
of
the users
are we very far away from that?
I think we are still not far away, but there are still some distance between the users' expected size. So right now, the user, I think they probably want to run a simulation on the quantum computer. So they want to scale, make sure your method can scale to larger and larger quantum circuits and larger quantum computers. So I think now we are there are some distance between our method and their request.
Thank you.
Thanks for the question.
Thanks for the nice talk. Your ZMapper framework looks to me quite similar to Maxat. So have you considered what the benefits and drawbacks would be of using an off-the-shelf Maxat solver?
So one of the baseline is based on the MaxSat-based approach, and that's even slower than our baseline TBOSQ2. So I guess probably firstly, their encoding may not be good, and the second, they do not benefit from the parallel solving. We may try a new encoding for MaxSat, and which may improve the solving performance, but I'm not sure whether MaxSat can benefit from parallel solving. Do you have an idea of that?
I don't know, but thank you for your answer.
Two last questions, and since I ignored the left side, sorry. So perhaps, and then Armin.
Just a comment. I think the TBLSQ2 is not optimal solver, right? So it doesn't guarantee optimality.
No, it's if you give infinite number time, it will finally reach the optimal value.
No, it's actually near optimal. Just to mention,
if you relax the depths and also the upper bound, finally it would reach the optimal value. It could be used as a near optimal solution. It can also be used as a complete solution.
I disagree, but it's okay. Yeah, thank you.
Yeah, so if it's okay.
Yeah, yes. So thanks also from my side. So there's a similar question also relating to the Moshe's question. So you can, this is anytime approach, right? You can stop anytime and be happy with this approach. And then of course it would be also interesting how long it took you to get the best solution before you prove optimality. Have you done this? How much faster is it?
It's very difficult to reach the optimal value. So if we draw the figure, you can see as we approach the unsat case, the runtime increases exponentially. So in most applications, we cannot reach the optimal value within the given time limit. But the user, they don't want the optimal value. They just want as close to the optimal value.
Thanks.
Yeah, thanks for the question.
Thank you for the very interesting talk, and let's thank the speaker again.
Thank you.
And now Fansha will now give the second presentation of this morning. Fansha will talk about optimal layout synthesis for deep quantum circuits.
Hello, can you hear me? Yeah, thank you. Yeah, thank you. Our topic is on optimal layout synthesis, but this is same as circuit mapping. So you'll probably have some. Oh, you can't hear? How about now? Yeah, perfect. Our topic is on optimal layout synthesis. This is basically same as circuit mapping, but we do it optimally. This is a joint work with Jaco van de Pol. And there has been a lot of hype about quantum computing. And quantum computing basically offers a new way to solve some hard problems. The main difference between classical computing and quantum computing is using qubits or quantum bits. So basically, classical bits have either 0 or 1, but a quantum bit can have it can be in a superposition in both 0 and 1. So some probability. Not working. Sorry. Yeah, how about now? Perfect. Yeah, thank you. Okay, I will just continue from here. So the main difference between a qubit and a classical bit is a qubit can be in a superposition of both 0 and 1. So you have some probability of being 0 and 1. So that's the main difference. And then let's suppose you want to solve some problem with a quantum computer. So you have to follow some compilation steps. So you start with a quantum algorithm. And then a quantum algorithm produces a high level quantum circuit. And not every processor can take this high level circuit. So you need to do a circuit synthesis. And through circuit synthesis, you generate a low level quantum circuit. And finally, before you can execute on a processor, you need to do something called layout mapping, layout synthesis. So this is the same as circuit mapping. So it has many names. And in this talk, we'll focus on layout synthesis. So here on the left, you have an example circuit in a low-level format. It's an open quantum assembly format. So it basically lists the quantum gates, how many qubits you have, what quantum gates you need to apply. On your right, you have the same representation in graphical representation, and each horizontal line represents a qubit, and these boxes represent single qubits. This interesting shape is a 2-qubit gate. So for this talk, we don't need to know what the gates do. All we need to know is on which qubits are they applied, on in which order they are applied. For example, the C1 gate can only be applied after H, but not before. So this dependency is important. Okay, and if you look at the complete adder circuit, it looks something like this. It has 10 2-qubit CNOT gates and 14 single qubit gates. Now let's suppose you have this circuit and you want to execute on a quantum computer. You need to perform something called layout synthesis. So if you look at the figure here, this is an actual picture of an actual quantum computer. And it has 5 squares. These are the physical qubits. Now the idea is to initialize the logical qubits on the physical qubits such that all gates are executable while respecting the dependencies. Now you can vaguely see that some qubits are connected, some qubits are not connected. So you can see a little bit better in this coupling graph. It just says which qubits can interact, which qubits cannot. For example, 0, 3 cannot interact. So now we can see that we can always execute single qubit gates, but not 2-qubit gates. So we'll update our problem. We say we want to map the logical qubits onto the physical qubits such that all 2-qubit gates are executable in the order that is required, but only on the adjacent physical qubits. So now let's try to do this mapping. Let's suppose we mapped L0 to Q0, L1 to Q1, and so on. This is a very simple mapping. And if you try to schedule C0 gates, you can schedule C1, C2, C3, and C5. C4 and C5 are parallel, so we can swap them. So now Q2 and Q3 are connected, Q0, Q1 are connected, Q1, Q2 are connected. So these are fine. But the problems comes with the C4 gate because Q0 and Q3 are not connected. 0 and 3 not connected. So now what do you do? So it turns out no matter where you map, you cannot actually schedule all the gates of this circuit because these 4 C0 gates form a square. But our platform does not have a square. So it doesn't matter where we initialize logical qubits, we cannot map it. We cannot schedule. So we use a swap gate. So now what is a swap gate? A swap gate is simply a sequence of 3 C0 gates. And what it does, it swaps the values of qubits. So turns out if we use a single swap, we can schedule all the C0 gates. So now what happens is you have L0, L2 mapped here, L3 mapped here. You schedule all these gates and you swap once and you can schedule everything else. Now at the end of the circuit, you have L3 here, L2 here. And turns out this is optimal number of swaps needed to layout map for this problem. Now, what is the problem? We can always do this, right? So we can come up with a polynomial time algorithm to schedule all the gates. You just go through one C0 at a time. If you find some C0 that is not schedulable, you just swap around and schedule all the C0 gates. So the problem is it comes with the noise. So we are currently in noisy intermediate scale quantum era, NISQ era, and every gate adds noise. And reducing this noise is key to practical computing. So directly reducing noise is hard. So what we do is we try to reduce the depth of the circuit, number of gates or error gates of the qubits. So in this paper, we focus on minimizing the additional swap gates. And in fact, we want to synthesize provably optimal swap counts, mappings with provably optimal swap counts. Okay, there are two lines of approaches. One is heuristic approaches. In major compilers like IBM Qiskit and Ticket, there are some such based algorithms which are heuristic. There are some other approaches based on A-star, temporal planning, constraint programming. These are very fast because we can always find some polynomial time algorithm to get some mapping. But the problem is they add too many swaps. This is not good if you want practical quantum computing. This is also not good for deep circuits. The other approach is exact approaches. They are mainly based on SMT. There are some swap optimal, depth optimal approaches. If you guarantee any kind of optimality, you will run into time and memory bottlenecks. So people propose to relax some constraints and make them near optimal so they can scale a little bit better. So TBLSQ2 is actually near optimal. Okay, and we actually have our own previous work. Our tool name is QSynth version 1. So we encoded the optimal layout synthesis as a classical planning problem. It was accepted at ICAD last year. So the idea was to encode the actions, either schedule a CNOT or when to swap 2 qubits. Now the goal is to schedule all CNOTs on adjacent physical qubits while respecting the dependencies. Now the interesting part is the optimal plan that you get from a planner corresponds to an optimal mapping because the extra number of swaps corresponds to the extra number of swaps that you need. They're actually optimal. And we have significantly outperformed existing tools by then, the QMap and OLSQ. And we used off-the-shelf planners, fast downward, and actually SAT-based Madagascar for optimal synthesis. We also won Outstanding Domain Submission Award at IPC competitions last year. Okay, so is the problem solved? Actually not. So there are many challenges. So if you observe a little bit, the number of CNOTs don't change. The only extra actions we have are number of swaps. So the optimal plan length would be the total number of CNOTs and number of swaps. So in our example, we had 10 CNOTs and 1 swap. So the plan length was 11. And in practical benchmarks, you can have hundreds of CNOTs and swaps can reach up to 20. And optimal planners suffer from scalability when you have long make span. So we want to solve this, and we propose SAT encoding based on parallel plans and incremental solving. So we have 4 key ideas. So first one is to use parallel plans to reduce make span, and then use two-way CNOT constraints for better dependency propagation, and then incremental solving to reuse some of the clauses that we learned, and use some redundant clauses to localize information. It seems to help CDCL solvers. Okay, I will go through one by one and give a little bit more information on these ideas. The first idea is to use parallel plans. So if you observe, we start with a mapping. We map our logical qubits to physical qubits. And we notice that this mapping only changes when we add a swap. So instead of scheduling each CNOT one at each time step, which we do in a sequential mapping, turns out we can group them. We can schedule them in the same time step. So this reduces the make span and avoids many copies of the variables. And then we want to relax this. We want to reduce the make span, but we don't want to give up the optimality. So what we do is at each time step, in addition to the group of CNOTs, we give exactly one swap. So we increment each time step with exactly one swap. So we are sure that we'll find optimal number of swaps. So the T is equal to the number of swaps needed. And here, this is our example. We realize that, okay, instead of 11 sequential steps, we only need 2 parallel steps with exactly one swap. And now these, so SAT solver doesn't need to order these C nodes in each parallel step because we can get this information from the original circuit. This can be recovered later with post processing. So we want to make SAT solver's life easy. And the second one, well, we don't need to worry about a parallel step, but we still need to encode dependencies in different time steps. So what we do is, let's suppose we scheduled a C naught in time step T. So we need to say that all the predecessors of this C naught can only be scheduled in this time step or any time step before, but not later. So this is enough for correctness. But turns out giving a little bit more extra information helps the SAT solver. So we also encode, if you schedule a C naught here, all its successors can be scheduled either in the same parallel step or later, but not before. So a SAT solver can figure out this information by some search, but turns out giving this information helps. And if you encode this naively, we will have encoding size quadratic in the number of C nodes, and C nodes can be in hundreds of C nodes. So we want to avoid that. So we use these auxiliary variables. So at each time step for each C naught, we have 3 variables: advanced, current, delayed. So we specify whether a C naught is current, advanced, or delayed to next time step. And then we have some nice clauses, and our encoding scales linearly with the number of C nodes, and we avoid long clauses as well to help propagation. And then the third idea is to use incremental SAT solving. Because if you want to synthesize a k-swap optimal synthesis, you need to refute all mappings with k-1 swaps. So for this, it's obvious that we need to use incremental SAT solving. So what we do is, in each iteration, we assume that no C nodes are delayed in the last time step. And if we don't find any mapping, then we increase the make span and we update the assumptions. And we keep on doing until we find some map. Okay, and the fourth idea, we remember that in the initial mapping, we need to map logical qubits to physical qubits. So this is the bijective. So you need to map uniquely, and this can be encoded with exactly one and at least one cardinality constraints. So now intuitively, this bijective mapping needs to be maintained in every parallel step. But the SAT solver it might not know. It needs some search to figure this out. So it turns out giving this explicitly seems to help SAT solvers quite a lot. So we also do this. So in general, we experimented quite a lot between levels of propagation, giving redundant clauses, and trying to have clauses in a different way. So a good encoding seems to require a balance between search and propagation. So what we did, we have a basic encoding, which if you remove a single variable, it will be an incorrect encoding. And then from there, we started adding some redundant clauses or some domain-specific information. And turns out it's obvious that if you give too much, the SAT solver seems to have trouble finding the answers. But if you give the right amount, they perform much better. It's 5 times better sometimes. So, okay, so we encoded all of these ideas in our tool. We extended QSynth version 1 to 2. It's an open source tool. And we use PySAT for cardinality constraints and access to incremental SAT solvers. By default, we use a sequential counter and Cadical SAT solver as a backend. Because we use PySAT, we can just change options and run other SAT solvers and cardinality constraints. So our input is a quantum circuit in OpenQASM format and a coupling graph, and we output optimally mapped circuit in OpenQASM format. For experiments, we took 2 tools, TBOLSQ2, which is near optimal, and then Sabre, it's heuristic. So Sabre and Ticket perform similarly. Sabre is by IBM Qiskit. Ticket is a different compiler. So we chose Sabre because previous papers in literature also compare with Sabre. And for benchmarks, we gathered, for the first set, we gathered all the standard benchmarks from previous papers. We have 23 instances, which have up to 54 qubits and can have up to 270 C nodes. And for the second benchmark set, we have some industrial benchmarks based on VQE. We have 10 instances with 8 qubits, up to 79 CNOTs. So these are from one of the companies I also work in. So basically, you want to find some ground state of some molecule. Apparently, they can use some excitation operators and then build some circuits and find them. So we took those blocks and randomly generated 10 instances of 8 qubits. So this is also our contribution. And for mapping, we considered 3 platforms: 54 qubit Sycamore by Google, 80 qubit Rigetti, and 127 qubit Eagle from IBM. And for the first experiment, we mapped the standard benchmarks to 3 platforms. And here we compared the additional swaps by TBOLSQ2 and Sabre. And the second experiments, we mapped the VQE benchmarks to the 3 platforms and compared the swaps and depth to the TBOLSQ2. For each instance, we give 12,000 seconds and 8 GB. We use single core. We give this high timeout just to see how we scale and how our competitors scale. So I have some results. For the first experiment, on the right, you can see our plot. So on the x-axis, this is our tool QSynth2. This is the time taken by our tool. And on the y-axis, the time taken by TBOLSQ2. And this bold line is x is equal to y. And these dashed lines are 10x and 100x speed up. So if any dot is above this line, we perform better. If it is below, TBLSQ2 performs better. So we can. So there are 3 types of dots. Depends on which platform it is. And here we can see that we can clearly see that we outperform TBLSQ2 sometimes up to 100 times. And for the first time, we optimally mapped several circuits up to 16 qubits onto these large qubit platforms for the first time. And Sabre, it's extremely fast. It maps everything in a couple of seconds, but adds way too many swaps. And here is a summary. So here we have 69 instances in total. Our tool solves 61 instances. All of them are optimal. And TBLSQ2 solves 56. 47 are optimal, but it doesn't know. Whereas Sabre solves all of them, but 10 of them are optimal. Of course, it doesn't know. And I will show one more data point from this plot. I think it's somewhere here. So this is a Quaco 16 qubit benchmark. Benchmark with 87 CNOTs, and it is mapped onto 127 qubit Eagle platform. And we show that, okay, we only need 4 swaps, which are optimal. TBLSQ2 times out. And Sabre requires 36 swaps. It's like 9 times more than what's needed. So each swap is 3 CNOTs. So this is quite a high number. This is not what we want. And for the second experiments, we have something similar results. In a similar plot, we can see that we also outperform TBLSQ2 again, sometimes up to 100 times. And for the first time, we optimally mapped 8 qubit VQE circuits. One of the instance needed 17 swaps, 17 optimal number of swaps. So it performs quite well. And then here is a summary. After 30 instances, we solved 24, whereas TBLSQ solved 20 and 9 were optimal. And we also compared the depths. Sometimes our tool also reports better depths. Okay, and beyond that, so you might have noticed that we haven't used any of the specific information of gates until now. But industry wants any reduction in CNOT gates. So we also give some additional functionality. These are all existing approaches. Turns out, you might have noticed that we have more physical qubits than logical qubits. So using these extra empty physical qubits seems to reduce the number of CNOT gates. So we give this as an option. Sometimes these extra qubits can be costly, so the users can decide whether they want to use them or not. And the second one, so sometimes swapping qubits is not, swapping qubits is not what we want. Turns out you can use something like a bridge. For example, if you want to connect 2 physical qubits here, only these 2 qubits are connected and these 2 qubits are connected. Turns out you can use such a gadget instead of a swap. So these are 4 CNOT gates, so you have 3 CNOT penalty. It's the same as a swap. But if you don't swap, turns out in some instances it helps. You can reduce the number of swaps you need, number of C nodes you need. And final idea is to use gate commutation. So for example, these two C nodes, the order doesn't matter. So you can commute them. And in some cases, you can avoid some swaps. So basically, relaxing some dependencies or these problem constraints can lower the optimal C node counts. So for all these options, we guarantee optimality for our encoding, assuming our encoding is correct. And we have experimentally showed that we indeed reduce the C node count, which is consistent with the literature. So conclusion, we presented a two-way SAT encoding and integrated into our QSynth version 2. And we have experimentally showed some scalability for deep circuits and mapped them onto large platforms. Future work might be experiment with other SAT solvers, perhaps parallel SAT solvers. It seems they work well, at least for this problem. And if you don't need optimality, for near optimality, you can start from some heuristic bound, upper bound, and then decrease the make span. So maybe some instances it might work well. And we actually have one more follow-up work, QSynth version 3 also out. So you have noticed that the number of single qubit gates and 2-qubit gates do not change in our synthesis. But we can also do resynthesis of these circuits and actually reduce the initial CNOT gates. So we did this in this paper. It's we took the properties of CNOT gates and did resynthesis, and we handled some extra properties that are interesting. And we encoded them in planning SAT and QBF. So here SAT and QBF performs really well. We also guarantee optimality there. Thank you.
Thanks a lot for this informative talk. Moshe, yes, the first.
Could you explain the relationship?
I think they are solving the same problem and similar techniques. The main difference would be they allow parallel swaps in each parallel step, so they don't guarantee optimality. They are guarantee optimal make span, but here we guarantee the number of swaps. And then the encoding sizes are slightly different because they have quadratic blow up in C naughts, and we have quadratic blow up in physical qubits. Usually swaps are much higher than physical qubits. We have to compare the performance. I couldn't find the open source tool, their version, but I don't know. Only after comparing. But from the results, I can see we perform better.
Yes, please.
Your example of the grouping of the CNAT gates.
Yes.
Maybe you can go to 13, I guess. Yeah, this
yes.
one. So I'm not sure. Here you assume the CNAT gates in between. You might have some single qubit gates.
Yes.
Otherwise, you will cancel out the CNAT gates here, right?
We have single qubit gate. Sorry, just for easy representation, I show this, but we will insert the single qubit gates again inside.
Okay,
in post-processing.
But if you insert a single qubit gate, can you say these four T equals 0 group is still you can do this in one step?
Yes, yes. We guarantee that by computing our dependencies.
Okay.
Yeah. If we have some problem, then we will say that, okay, it can't be in the same time step.
And in your experimental result, you didn't show you have additional functionality, right?
Yes. Nope.
So you have some experimental results for this in the paper?
In the paper, yes.
Okay.
I didn't present it here.
Yeah,
Perhaps I may ask a question. So could you just, so I don't have any feeling for the environment. So I intuitively would think, oh, it's hardware. Okay, why not compiling it for 10 hours? Because but possibly you want to run it only a few seconds. So could you explain a little bit how that environment, how does it look like, the real world application, or is everything currently experimental?
Well, we have one of the papers released now in one of the companies I am working in. We simulated the breaking of No. Right now it's only one. Yeah, it's a quantify. It actually works with the quantum computing applications. So the idea is that we want to get optimality so that we reduce the noise as much as possible. So it's fine if we have 10 hours of compilation time. So the main problem is what happens in the quantum computer. So we recently ran one of the bond breaking simulation in the physical quantum computer, and there we also use our compilation there. So usually you only run for 10 minutes in a quantum computer. You don't run longer. So then you get some shots out and you do some post processing for the application. Yeah, but compilation can be any long. It doesn't matter.
Final questions, please.
Yeah, so you mentioned that we can use bridge as compared to swap over here,
Yes.
right?
Yes.
But swap, as you said, it only has 3 CNOT gates, but bridge has 4. So how is this better?
Exactly. So swap doesn't satisfy any CNOTs, but bridge satisfy one CNOT. So it also schedules this CNOT implicitly, right? So the extra number of CNOTs are 3 plus 1. So we are also satisfying one CNOT at the same time. But the swap just swaps around. It doesn't satisfy schedules any CNOT. So the additional cost is same.
Sorry, we have also one online question, so that let's be the final question. But before you head off, then we have some important announcement and a few more rewards after that. So, but first, if you can get the online question.
Hi, can you hear me?
Yes, we hear
you.
Yeah, thanks for a great talk. Maybe a follow-up question of your previous question. I think the TPU-SQ2 can be used as an optimal method if you relax the number of the steps to be greater than the swap count, right? At that time, you can prove the optimality. But in most cases, you don't need to relax to be that large.
So, I mean, we let the TPU-SQ2 run completely and it stops and we present the same results. So we actually show that there are many instances where TPU-SQ2 is not optimal.
Yeah, I just want to see like if you slightly modify TPU-SQ2, it can be used at it finally degenerates to OSQ2 if you further reduce further relax the steps.
Yeah, we were in touch with the authors. We have made sure that it's actually near optimal. So, the others agreed. Sorry.
Okay, we can take it offline.
We can take that offline. Yes.
Yeah.
It's okay. Yeah.
My question is like, have you found like what kind of computer or what kind of the quantum circuit you found is easy or hard to solve by your method?
Yes. In general, anything beyond 50 is hard. If you want optimality, it's extremely hard. 16 qubits can be doable.
Yeah.
But yeah, anything beyond is hard. I think you need to do slicing. So you make subcircuits of the circuit, and then you map optimally for these slices. Yeah.
Thanks. Thanks for the talk.
Thank you. Let's thank again. And as I said, please don't run away.
All right.
Now.
Thank you. Thank you so much, Oliver. Right, here I am again, but this time with a different task. Who all were there for the banquet dinner? Show of hands. Who all heard what Venki said in his speech there? You know, whenever we try to name or make a list of people that we want to thank, it's very likely we'll miss out on someone. And that's what has happened yesterday. We missed out on some very important people. You know, we missed out on felicitating them who have really worked hard, who have really contributed in making this conference a success. So I'll request Professor Moshe to please come on the stage and felicitate them. I'll call out their names, requesting them to please come